Hi everybody, I'm going to go over how to find the most acidic proton in a molecule in this video. So the first thing we need to do is we need to find the conjugate bases that are possible and then compare them, okay? So that's basically what this list is telling us to do. And we want to keep in mind that we remember that the most stable conjugate base is going to come from the most acidic proton, okay? The easier that proton is to lose, that means that that conjugate base is going to be more stable to get to, or more stable to stay in. So the first thing we want to do is draw out our hydrogens so that we can find our protons. So we're looking at this one, these, and that. And then I've got the H's on the oxygen. I'm actually going to do those in black. I should have done that to begin with. Okay, so once we have all of our H's drawn in, then we can kind of rank them in terms of similarities, differences, and we're just gonna do a light kind of ranking here. We're not gonna go super hardcore, but we just kind of want to get an idea of where things are different, so that we kind of know how many options we should go through. So I'm gonna label these out a little bit. So the H on that oxygen over there, I'm gonna call A. I'm going to call this one B. These two are going to be C. These two are going to be D, E, and F. Okay. So if I'm going to look at every single one of these, I essentially have those 1, 2, 3, 4, 5, 6 options, A through F. So that means I'm going to draw out 6 conjugate bases. Okay. So if I go to HA first, right, do my conjugate base, my acid base arrows. That's my conjugate base. Do I have any options in terms of resonance here? I really don't, because I can't forget that I have this H right here. So I can't really go anywhere with that. It is localized. Okay, so let's go ahead and look at B. And there's really not a whole lot that you need to do when you're drawing these out. You just kind of want to be looking to see if resonance is an option and just kind of draw those out as you come across them, or you can draw them out at the end. It doesn't really matter. So in this case, I do have resonance. I can go here and then up onto the oxygen. Okay, so then I'm at this point. Can't really go anywhere else, right? I can't go this direction because then I'd overload the octet on the other oxygen. I can't go this way because then I'd have too many bonds. I'd be breaking some rules if I did that. So this is basically the only thing that I can do. So let's go ahead and look at C. C is surrounded by sp3 carbons. It's localized. Okay, let's bring in other colors here. Let's go with blue. So for D, let's point it at H. Okay, so for this one, I do have that lone pair next to a pi bond, so I can do resonance here. Go there and then there. Pi bond there. And then I'm still next to another pi bond, so then I can go up onto the oxygen. To end up here. At that point, I'm pretty much done. Okay, so that one was a pretty good one. I got a few resonance structures out of that. So let's go ahead and go with pink. And look at HE. Okay, so I've got my negative charge on that oxygen. Got the 3 lone pairs. So then I can have resonance using that pi bond. Put the lone pair on a carbon. End up here. I'm still next to another pi bond, so I can use that one. And then put it onto the other oxygen. At that point, I'm pretty much done. So that was another good run that I had. And then let's take a look at our final one, HF. I hope this is going to be visible. No, it's not too bad. Okay, so once I'm here, if I'm looking for what I can do in terms of resonance, I can try to do this because it is next to that pi bond. Let's just see what that gives us. So that has made us run into an issue, right? This wants to be sp with a bond angle of 180, which makes that molecule quite sad. Okay, so this is not reasonable. Okay, that would be a pretty localized charge. So this is localized. Okay, so now that we have all of our options, we kind of need to go through and start discarding some of the ones that are just not as good as the others. So let's go ahead and start. Trying to figure out which color to use. Okay, so anything that's just kind of localized on a carbon, I'm gonna not care about. Okay, so localized on a carbon, we're gonna throw that away. Delocalized on a carbon. Oh yeah, this one, another one that's localized on a carbon. Okay, so that allowed us to throw out 2 of them. And keep in mind, I'm showing you like the full run through of this. You do not need to draw out every single conjugate base that is possible. If you can see, oh boy. If you can see this situation here and go, well, that's not going to give me anything reasonable, don't draw it out. You don't need to. But if you're still trying to get the hang of it and you need stuff drawn out, then don't be afraid to draw it out. It's really not that bad. Okay, so now let's just kind of make a list of what we have going on here. So there's a couple of ways that you can do this. Sometimes I really like to do the resonance hybrids, and sometimes I just make a list of where the charges are, okay? So we're just gonna go ahead and make lists. So negative on O, it is localized on that oxygen. This one we had a negative on carbon and O. That one we got rid of. This one we had a negative charge on carbon, carbon, O. The pink one, negative charge on oxygen, carbon, oxygen. And then the final one we crossed out. Okay, so from that, you can see pretty well how you would rank these in terms of, you know, these two might be fairly similar, but there's a clear winner here. Okay, this one is going to be the most acidic with the most stable conjugate base, because I've got charge delocalized on 2 oxygens and 1 carbon. That's going to be way better than 2 carbons and 1 oxygen, and better than 1 oxygen alone or 1 carbon and 1 oxygen. Okay, so that means that HE is the most acidic proton here. Because it gives us the most stable conjugate base. Okay, so that's really what we're looking at here, is being able to identify our options and then look to see which one is going to turn out to be the best. So got to make sure your resonance structures are on point. So as always, hopefully this helped. Please let me know if you have any questions, and I will see you all later.